the radiation and the convection zones of a star, and why we call them like that. But in here, just remember that the sun has a core, 200,000 kilometers of radius. You have a radiation zone, 300,000 kilometers, and you have, again, a 200,000 kilometer radius of convection zone. Okay? The main idea is how energy is propagated. Okay? Convection zone, we call it convection because we have convection currents. If you remember from the greenhouse effect, guys, or the water cycle here on Earth, in the convection, warm material goes down, cooler material goes up, right? Or sorry, cooler material goes down, hotter goes up, right? So you have a convection cycle like that, right? Warm air goes up, cooler air goes down. In the convection zone of the sun, you have higher radiation going up and then cooler one recycling it. So as it approaches the radiation zone, it warms up again and it goes up. Why is the sun in equilibrium? Well, any star that you see in the night sky is in equilibrium. We call it a hydrostatic equilibrium because there's an equilibrium between the gravitational pull of the sun itself and the radiation pressure, or the pressure, the outward pressure by the nuclear fusion happening in the core. Okay? So when we talk about the origins of the solar system, guys, one of the keys was that the protostar, or the protosun, will ignite into a star. When does the star ignite? When hydrogen starts to fuse into helium in the core. That provides enough energy for equilibrium to happen. And this equilibrium, in the case of the sun, will keep going on for 10 billion years because the hydrogen is being depleted at that rate. Now, we can see solar spectral lines as we see solar vibrations. You see, there is something called solar seismology or helioseismology, where we analyze how the spectral lines of the sun change by vibrations happening in the interior. You see the sun and you think that nothing is happening, but the sun is rotating. It has a period of rotation of about a month, and it's also vibrating. Why? Because of these forces that are acting in the interior. And because of that, we can see Doppler effect. The idea of Doppler effect, guys, is what you see there, blue or red. Whenever you see the sun, you see emissions of wavelengths, right? Electromagnetic waves. These electromagnetic waves may change their frequency and wavelength as these vibrations are happening. That's when we talk about Doppler shift. Now, why you see blue? Blue is when the wavelength becomes shorter. Red is when the wavelength becomes longer. Okay? And what are these spectral lines? Let's go to here. How do we know the composition of the sun? Right? How do we know the sun is mostly made of hydrogen and helium? Because we can use a spectrometer attached to a solar telescope to analyze the light incoming from the sun. And this is what we find. We find a lot of elements in the atmosphere of the sun. The most relevant is the hydrogen alpha and helium lights. That's the ones that we see the most. These are gaps in the solar atmosphere. You see, if there were no elements in the atmosphere of the sun, this will be a continuous spectrum without these black gaps. We see these gaps because of the elements that are in the solar atmosphere, in the sun's atmosphere. Going back to the energy transport. So the radiation zone, which is outside of the core, basically electromagnetic waves like this, is kind of transparent. While the convection zone, you see the convection cycles in that, is actually opaque. Now, on the surface of the convection zone, on the outwards, is where you find the photosphere. You see, the photosphere, guys, is basically what you see when you're looking at the sun. Of course, with a solar telescope or with sunglasses, never look at the sun directly, guys. All right? But whenever you see the sun, you are seeing the photosphere, which looks like these granulated layers here. Okay? That is the surface that is at 6,000 kelvins of temperature. That's the surface of the sun. On this area is where you actually observe this. Do you guys know what this is? I mean, yeah, you should know. That's a sunspot, right? Why do we care about sunspots so much? We care about sunspots because they tell us a lot about the activity, the magnetic field, and the activity of the sun. You probably have heard about NASA or astronomers in general, always tracking down the number of sunspots that are happening on the sun in a given period of time. And sometimes they correlate with solar mass ejections, with solar storms, which happen in the chromosphere, by the way. That's the surface, that's the layer on top of the photosphere, by the way. You have the photosphere, you have the chromosphere, and then you have the corona. All right, the corona of the sun is around here, is the outer atmosphere of the sun. You have the photosphere, the surface of the sun, the chromosphere, a little bit beyond the photosphere, and then you have the corona. The corona, guys, is that. We can see the corona during a total solar eclipse. All right? It's like a halo surrounding the sun. Very hot. Look at the temperature scale or temperature curve. In the chromosphere, so in the photosphere, you're at 6,000 kelvins, right? In the chromosphere, as you will expect, the temperature decreases. Then there is a transition between the chromosphere and the corona. And then in the corona, you again go to about 1,000,000 kelvins. This intrigues physicists and astronomers a lot because you will expect that the farther you are from the core, the lower the temperatures. And that makes sense in the chromosphere, but you don't see that happening in the corona. And the explanation for that is that in the corona is where you have solar mass ejections. So there is a lot of activity in the corona, which require a lot of energy. There. Because of these eruptions that happen, you may actually expect the temperature to actually increase. All right. You probably have heard about solar mass ejections, solar flares, right? These are explosions happening on the surface of the sun and that are emitting energy in every direction. Remember when I show you guys the video of the auroras? Well, basically that is what happens, right? You have an explosion on the surface of the sun that may be able to escape the gravitational pull of the sun and eventually reach every planet, especially every terrestrial planet. When it reaches the Earth, that's when we start having those auroras in the north and the southern hemisphere. So sunspots, guys, we can track them because they can come and go. Maybe because of the rotation of the sun or because of the solar activity. Sunspots are linked to magnetic field lines, guys. You see the magnetic field line can enter from the north or goes from north to south like that. So you may have magnetic field lines that are entering and leaving a sunspot. And when you have an spicule or a solar flare, they can easily trace the magnetic field in between sunspot and sunspot here. That's why I said that we use sunspots to track solar activity on the surface, right? And why do we track it? Because of solar storms. And why do we care about that? Because of telecommunications or even the weather, right? Strong solar activity can trigger changes in our weather. Okay, I talk about the production of or the activity of the sun, right? So the heart of the sun is the core, which has a lifetime output of 3 times 10 to the 13 joules per kilogram, right? This is allowing the sun to live for roughly 10 billion years. Now, this energy output can be measured with solar panels, right? And we can use them, right? We have started to use solar energy. Now, where does this energy come from? From the core. But how does the core work? By nuclear fusion. You have nucleus 1 plus nucleus 2 in a nuclear fusion, giving you a heavier nucleus and emitting energy. Where does the energy come from though? Well, let me explain basic nuclear physics. Well, if you have hydrogen and then you get a heavier nucleus of hydrogen here and energy, believe it or not, the mass on this side of the equation is different than the mass on this side of the equation. Not all the mass becomes nucleus free. So, hey, wait a second, that's against conservation of energy and mass. Well, not really. What Einstein discovered with special relativity in 1905 is that the mass difference is used by the speed of light to produce energy. We call that the rest energy mass relationship. So the mass difference multiplied by the speed of light squared give you the energy output of that nuclear equation. Okay, that's the Einstein's equation, right? N E equals to mc squared. So that's basically what happens. The mass is actually conserved. It's just that some of the mass becomes energy. That's the energy mass relationship. There it is. What this equation is telling you is that a small amount of mass is equivalent to a large amount of energy. Yes, because this amount of mass, which is not a lot, multiplied by the speed of light squared, give you a large amount of energy. Now, that's just for one reaction. There are billions of these reactions happening per second in the sun. And what do those reactions look like? Like this. You have 2 protons, basically 2 hydrogen nucleus, coming together, giving you heavier hydrogen. Heavier hydrogen is actually deuterium. We call that H2 and then H3. And they emit a positron, an anti-electron, and a neutrino, solar neutrino. This is known as the proton-proton reaction. In physics, we call it a PP chain reaction. Why do we call it a chain? Because this is what it looks like. Proton-proton, deuterium, it can recombine with another proton you get helium-3, and this helium-3 can recombine with another proton to give you helium-4. In every part of this chain, you get a reaction that emits energy, sometimes in X-ray forms, sometimes in neutrinos. That's how we can detect solar neutrinos, right? These are very hard to detect, by the way. Detectors for solar neutrinos are normally found underground, okay? So going back to this, hydrogen 1 plus hydrogen 1 give you deuterium plus a positron plus a neutrino. This positron is antimatter. Antimatter with matter, what it gives you? Energy.